Welcome to the next lecture of control system series. Today we are discussing about the transfer function of an AC servo motor, because in the before class we discussed about the transfer function of a DC servo motor, but today we are going to discuss about the AC servo motor. Why? Because when we are dealing with the DC motor, the parameters and the what are the contradictions, what are the ripples and everything, that will be a little bit of less compared to the AC. So, but for regarding that thing, we need to see the AC also. So that for regarding that, it is saying. So the AC servo motor will be in this way. Okay, and the topics to be covered in this lecture will be related to first what is AC servo motor, and after that what is the transfer function of an AC servo motor, how it will be designed, and what are all the parameters it need to be covered in that one. Okay. And when it comes to the AC servo motor, so AC servo motor basically it is a different thing which is used in a very high efficient and also high performance based equipment based things like robotics and also aerospace automation, and also where the things it can be easily able to control, and also precisely it need to be controlled. Okay, so if you see this one here, it is having the two wires, right? So those two wires are related to the, one is related to the encoder based thing, and one is related to the motor control or motor operate system features based, giving the feedback to the controller which can be able to control. Okay, so in AC servo motor, it will come under a normal here special purpose motors. Normally we have the motors like it as a AC motors, DC motors, and after, and also we have a another type of motors also, they're called as special electrical motors or special purpose motors also, we can say, where it can be able to control the angular position very precisely based upon the velocity and acceleration, each and everything can able to done. The thing is, it is works usually based upon the closed loop operating system, not in the open loop operating system, and it can offer a very high speed also. It can operate with even a low speed also. It can able to done. Okay, so this is what it can able to do, but it will get with a very high accuracy. That is the one of the biggest advantage compared to the DC servo motor. So when we see the key differences between the AC servo motor and the DC servo motor, how it will be there means, so unlike the DC servo motors, AC servo motors will work with the AC voltages and AC current. That means sinusoidal was AC, sinusoidal current and sinusoidal voltages, and they are also it becomes a brushless. So that's why they can able to get a high efficiency, and also the what is the thing is. The control algorithm, whatever we are going to design, that will be little bit of sophisticated, which is for the AC servo motors. But when it comes to the DC, the control algorithm will not be that much sophisticated. It will be a little bit of less. And the next is the modeling assumptions. As we already know, whenever we are going to design a transfer function of any motor or any electrical equipment, we are assuming some of the assumptions to make the transfer function to be or to understand or to get the mathematical equation very easily. So regarding that, we are having some modeling assumptions. So that is, so first of all, what are the assumptions we are going to take is the whatever the motor we are going to consider, that motor will be and comes under the two-phase permanent magnet synchronous motor, and the whatever the excitation, that means as we already know, the motor need to run means we need to give the excitation, and that excitation will be comes under the sinusoidal excitation and also small signal linearization basic principles. And we are neglecting some core losses, because when we neglect the core losses, we can able to easily get a current voltage equations and each and everything. So it will be easy to make the system control, and also not to get very in depth of more sophisticated control algorithm. And the next one is the modeling foundation, because when we are dealing with the AC based equipment, anything like not only the motors, whether it can be you are dealing with the AC AC converters or AC rectifiers or AC inverters or whatever it will be. So then what we need to do is we need to get a primary understanding about one topic, that is called it as a transformation techniques. Okay, those are called as Parkes transformation, inverse Parkes transformation. That means ABCT will be converted to the alpha beta converted to DQ axis. So because of these things only, we can able to control the whatever the parameter it will be. The parameter can be a voltage, the parameter can be a current, the parameter can be a power, the parameter can be a speed, the parameter can be some other things also, angle of the position, whatever it will be. So because we are transforming all the related parameters into one reference axis, like it is, whether it can be D axis or Q axis. How exactly these things can be done means with respect to the formulas which are derived from the Parkes transformation and inverse Parkes transformation. So to do that one, you need to know about these two things: Parkes transformation and inverse Parkes transformation is very important when you are reading with the AC based terminologies. And the next thing is electrical equations with respect to d axis, because we are going to deal with the both d and q separately, because one is related to the active, another one is related to the reactive component. So that's why. So the d-axis voltage equation, how it will be there means, if we are deriving that one, it will be related to the resistance and inductance of the d-axis, and also whatever the angular position of the total system or the motor. And in the same way for the q axis, we are having the same, but with respect to the, we are having some inertia and everything also, it will be comes into consideration. So that's why we need to consider the q axis, which need to be reduced to, or to maintain the zero. Then only we can able to get a very precise control. And the next one, these equations, mostly what we can able to do is it can able to derive the current dynamics. That means voltage not will be changed, but the current can able to change with respect to the load. So that can be easily can identify with respect to these equations. And when it comes to the torque equation, we have torque equation, right, with respect to poles and also the flux linkages and also current axis. So regarding that one, the torque equation is equal to 1.5 into P by 2 into the what are the flux linkage and also the IQ, Q axis current component. Okay. And the next thing is when it comes to, but we need to consider the mechanical dynamics also, because in the whenever it comes to the AC, we are going to consider for a motors both electrical parameters and also mechanical parameters. So regarding that thing, we need to consider that one. So the when we need to apply a Newton's second law of rotation, as we already applied in the before times also, which has it comes under the moment of inertia and also viscous friction, both need to be applied. So this will connect the electromechanical torque, electromagnetic torque to speed. Okay, you need to understand like it is, we need to consider multiple parameters here to, because whatever the control it can be controlled easily when we get all the parameters into equations. And the next one is when you need to transform this equations, all the above equations, to the Laplace transform which is needed. So on transforming equations, we already know we are having some initial assumptions like the initial conditions to be as zero. Then when we apply that one, then automatically the Q component will be equals to the voltage component, and with respect to the angular position and resistance and inductance which is fed into that one, and also with respect to the above uh, torque equation, we are having the same, it will become under. And when it comes to the transfer equations with respect to speed to voltage, before we discussed about the position to that one, now we are going to discuss about the speed to voltage. So now what will happen is when we transform all this mechanical equation, then automatically we know output by input. So then automatically it will comes like this. So rho, omega is 2 by VQ by S, that equal to 1.5 times of torque equation with respect to this one. But when it comes to the same thing, this is a what we call it as it's a second order function, because the whatever the higher order that with respect to the S is S square. So that's why it is related to the second order, and it related to the Q axis, not the D axis. And in the same way, in the position to voltage control, what we are having is we are having the, to get the position, we need to divide by S in the total equation. Then automatically what will happen, the equation will be shifted to the third order system, because S square will be converted to the S cube. So the system will get more sophisticated. When it becomes a third order system, we can't able to get control very much easily. It need to be a little bit of difficult. So to make the third order system to a little bit of reduced system, we need to consider some of the assumptions like that. We need to neglect some electrical time constant. So then automatically what will happen is it will be reduced to the second order system by this one. So whenever we are reducing the electrical time constant, so we will get this equation. And finally, this transformation, this transfer equation will help to control the speed and also position of the motor, and also whatever the speed voltage, each and everything can be able to fed to the motor. Okay, which can be done through PID and also state feedback things and else and everything. It can able to easily identify the real time monitoring system. So this is how it will be operated. And the next thing is application areas, wherever we are applying this one, that is also important to know as an engineer for that. So the AC servo motors are mostly used in the robotic arms, aircrafts, 3D printers, because they need a precise control, precise inch by inch or whatever the angle, what degree to degree it need to be controlled. So that's why we need to get each and every things into consideration. Okay, thank you.